Here we go. We have a lesson on linear versus angular velocity. Now, linear versus angular velocity is exactly what it says it is. Linear velocity would be velocity in a straight line. Angular velocity would be the amount of rotation per amount of time. So if we take a look, we have some formulas here. V equals S over T. Now that's going to be in length per time versus angular velocity, which is theta per time. That's going to be in radians per second. Then, of course, we have S, which is arc length. Arc length is going to be in radian lengths. And then, of course, we have linear velocity, which, of course, is going to be length over time again. This last formula is nothing but a combination of the previous formulas. So let's take a look at the kid on the merry-go-round. Now, if we have two children on a merry-go-round, we begin spinning the merry-go-round around and around and around. We talked a little bit previously when we were talking about the difference between radians and degrees. Degrees is going to be the amount of rotation that this kid here in the middle sees. Radians is going to be the amount of circumferential lengths that this child moves around. This kid is moving, this kid is just turning. And that's the heart of this discussion, because linear velocity is going to be how far something goes in a certain amount of time. So in the case of the outer person, you have a linear velocity of the outer person, and you have the linear velocity of this kid who's just spinning around right where he is, linear velocity of the inner person. And we know that the linear velocity of the outer person is going to be a whole lot more than the linear velocity of the inner person, because the inner person is going nowhere. All he's doing is spinning around. He stays in the exact same spot but spun around. This person travels however far it is around once, however far it is around twice, however far it is around 3 times. This kid still hasn't moved, even though he's just spun in circles. So the idea with linear velocity is it's going to be related to the radius. The kid in the middle has a radius of 0. The kid on the outside has a radius of whatever the radius of the merry-go-round is. Now, let's actually put a couple things together here and give another formula. If we have V equals theta r over t, all I've done is I've taken the equation for S and put it in to the equation for V. Now this makes a whole lot more sense, because if we do the outer person, that means his velocity is going to be in one rotation. It means it's going to be 2 pi, because that's how far he's going to go. Let's assume the radius here is 6 feet times a radius of 6, and let's say it takes all of 3 seconds to get around. So in this case, we're going to end up with 12 pi over 3 foot seconds. Now, for the person on the inside, he's still going to turn around because he's turning as fast as this person is turning. If the merry-go-round goes all the way around, the person on the inside is going to go all the way around just like this guy. So it's still 2 pi. And it's still going to take 3 seconds to accomplish the process. It's just if the kid in the middle is standing in the very middle, he's not going anywhere, and therefore his radius is 0 feet. And so his linear velocity is 0 over 3 feet per second. And so it's very clear numerically that the person that is farther away from the center is going faster in terms of how many feet they're covering per time than the person in the middle, because the person in the middle hasn't moved. Now, let's add another person here. We'll make them a girl, and it'll be velocity in the middle. Now, this person is standing 4 feet from the center. So in that case, if we want velocity of the middle person, we would take 2 pi, because we're going around just the once, times 4 feet, and it's still going to take 3 seconds. In which case, you come up with 8 pi over 3 foot seconds. Okay? So the clear indication is the further the person is from the center, the faster they're going to go in terms of linear velocity. And we've all felt this. If you've ever been on a merry-go-round, if you're somewhere near the middle, it may not feel like you're going very fast, but if you're on the outside, it feels like you're going faster, even though you're rotating at the same speed as anyone else. Because of the larger radius, you're actually going further around the circle than the person on the inside. So, with that, that's linear velocity. The kicker for angular velocity is it's simply omega. So it's omega has a little loop in the middle. Omega is theta over t. Now, in all of our cases, the omega for all of these is exactly the same because they're all going one rotation. No one's running around the merry-go-round. No one's running against the merry-go-round. They're all going one full rotation in 3 seconds. And in this case, you'll notice there's no feet up here, so it's radians per second, and it's 2 pi over 3. And that's true for the person in the outside, the person on the inside, the person in the middle. So it's all the same angular velocity, even though the linear velocity is significantly different. Now, let's build a couple of these formulas. Now, you'll notice I took v equals s over t, but s is r theta. Well, that's fine, except that, wait a minute, theta times r, if we have omega, okay, omega is theta over t. So what I come up with is if omega is theta over t, I can replace theta over t with omega. So now v could either be s over t, or it could equal theta r over t, or it could equal omega r. But in all cases, omega stays exactly the same. That is theta over t. But this is only true for radians because radians has to do with distance around arc. Versus your arc length, which is, of course, theta r, again, only in radians. So, if we have a few of those, then we can do a couple examples. One other quick note before we get to some homework examples is they could tell you things in terms of revolutions or rotations. So if I have 3 rotations, don't overthink it. All you have to do to get from rotations to radians is say 2 pi radians equals 1 rotation. Rotations go away, you're left with 6 pi radians. Well, that works out nicely. What if they give you 20 RPM? Okay, well 20 RPM is really 20 revolutions per 1 minute. So it's revolutions per minute. Well, okay, fine. I can change revolutions per minute into angular velocity, but remember, angular velocity is theta over t. It's radians over seconds, so we can't have revolutions per minute, per time. We can't have revolutions per minute, so what we do is we simply take this and say 2 pi radians for 1 revolution. The revolutions cancel out, and you're left with 40 pi radians per minute, which is omega. So paying attention to your units is going to tell you which one of these formulas you have. If you have feet per second, that's linear. If you have radians per minute, that's going to be angular. If you have straight up radian feet or radian miles, it's going to be arc length. Linear velocity, again, you're going to have radian feet or radian minutes, but then it's going to be times a certain number of feet. So you have feet per minute, and it goes on and on watching your units. So then we'll get to some examples. Here we go, a couple things to work on. If I have 4 pi over 3 radians per second, let's find revolutions per minute. Well, in this case, I need to get rid of the radians and get back to revolutions. So I'm going to say 1 revolution over 2 pi radians, cancel, 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 reduce, reduce. I come up with 2/3 revolutions, but that's still per second. So I have 2 revolutions per 3 seconds. And I would say 60 seconds per 1 minute. And I get rid of the seconds, and I come up with 120 over 3, which is 40 revolutions per minute. 40 revolutions per minute. Now, if I have 60 meters per second, but I also have 20 revolutions per minute, I want to find a radius. Well, how do I find all this? Well, 60 meters per second, I have V equals angle times R over T. Now, if that's in meters per second, I know that's 60 meters per second. I know that I have, well, let's do this, revolutions per second. If I have 20 revolutions per second, that means that I have to get to angular velocity. To get to angular velocity, I would need to take 20 revolutions per second, and I'm going to multiply that by 2 pi radians over 1 revolution, and I come up with 40 pi radians per second. And so my best formula of all 3 of the formulas would be to use, since I already know that omega is radians per second, use this formula and say 40 pi radians per second times, then we have time, or so we have radius. So all I have to do here is divide both sides by 40 pi radians per second, radians per second. The seconds are going to cancel out. You reduce this, you come up with 3, you come up with 2, and you have 3 over 2 pi, and that's going to be meters over radians, and that's going to be your radius. So all it is taking the various numbers, turning them around, spinning them about, finding what you don't know, picking whichever formula makes the most sense for you to use. Okay. Just in case you didn't catch the video that goes along with that audio, here is the video that goes through how to find each of these components, picking the right spot. Now, last example to go over, I want you to find the linear velocity and the angular velocity given 5 revolutions or rotations per minute, and this person is 4 units from the center, 6 meters from the center, 9 meters from the center. So I need to see 3 linear velocities, and I need to see 3 angular velocities. So find those 2 pieces.